So, continuing that discussion, we'll break it down into bits and pieces in terms of there's a sensitivity related to atmosphere surface coupling. What would that be like?
No. It's just that when we broke
early, too early?
Too early, and there weren't food out there for people. Now the food's out there, so maybe we just take a class and get them to, we can bring it in, have coffee or whatever.
Sure.
Just to,
I think every half hour. Let's take a break every half hour.
So this is the, tomorrow I should remember it's free again.
Oh.
That should be changed for future stuff.
非脑膜体质的工程度不一样。
哎，有一个地方你们听明白了吗？他在松动的那个400标还是800标做的，他就500那个是吧？这样说那样，后边气换的水汽在400标的情况，就是力很大的连带水汽。然后到这样的气温多的时候，它两个窗户里面那两个是什么时候？没
是做BRDF 讲看你是不是因为这个你不同非脑膜体不同角度的话，它反射不一样。
对，不同的角度它得到的反射率不一样，就反射不一样。
那它怎么做？它脑膜体它是做 BRDF 角度，它怎么去讲？
你看测试角度，它就测了好多那个，
就研究测角。
对，因子啊，像 BRDF 因子。
其他的是那比如说它的全部基本Don't worry. It's really cool. I like it. It's interesting. Besides the things that I usually get other people to do.
People like you like it.
There you go. But at the same point, when the data we got wasn't great, had to kind of go and try and understand what's going on. This helps tremendously. So, yeah, thank you again.
I'll get the chance to do a picture. Somebody always asks me, doing this teaching? No.
Maybe every now and then.
It's fun to do, but miss it.
It takes so much time.
I mean, even this, I'm putting in 1/10 of what I would want to do. Right?
But even so, it's I think it's so basically, do we need to use the laptop to transfer from that to the drive? So IT guru, you really sort of it exists. You just ultimately, yeah. Which is why I'm almost trying to make sense just from my laptop and then have it transfer huge amounts of data.
Well, you have a lot of space.
Yeah.
We got that. Maybe we can do it.
Sure.
Case.
Since you're the one that actually needs to look at there.
Each and every morning I could go for a run across the hall. And the coffee was done, so
I would say I'm here because it's cheaper. It's also very interesting. But I have help whatever I can.
Yeah, they optimized.
Oh,
Right.
so Microsoft is not going to be able to go too extensively, right? But I have validated empirically these small that I thought might have been just now that we're aware of it, we'll take the same approach that we did with the
Which was?
constantly tell him to go take a shower. And he did. Super soakers were threatened.
So we're going to continue on this discussion of sensitivity analysis, and there'll be some more examples of some studies of sensitivity, but related to different bits and pieces of the reflected space problem. So in this case, it's now looking at things that might be related more towards how the atmosphere and surface couple with each other. And this goes back to the discussion I was making in terms of the site comparisons and the results of the different sites, because you have different size sites with different features and physical processes, and what's going on between large and small site results for 8 different days. Somebody was asking, it's days since launch. These data points here, day 500 of Landsat would be roughly in late 2000. So, giving you an idea, this is old data, but the results don't change much over that time period. But you look at the difference between the large and small test site data and the results. And what you see is there's not much in terms of our band. You have band 3, band 2 of best. This is basically the red band. This is the near infrared. And then you get out at 1.6 micrometers, the shortwave infrared. And then slightly longer, 2.2 micrometers, the Landsat band 7 and the Astra band 6. And you just start to see that there's not something very noticeable in terms of the results as a function of site. There are a few data points for Astra that look a little bit larger than what you might expect, but you're not seeing much in terms of the difference in the test sites. And this again was, when we did the rate to transfer discussion earlier, led to that type of answer as well. And this is just that plot I showed before of the large sites Pima County Fairgrounds. And the small site, this is Landsat. No big difference. And I ended up, before we took the first afternoon break, before this recent afternoon break, that 2, 3, and 4, we were seeing significant differences between the large and the small site. And again, everybody was saying, well, that must be because of adjacency effects. And I brought the magic reflectance because we were pretty confident that it was not an atmospheric effect because of this. The adjacency effect is minimized to some extent because of this as well. But it is something that maybe they were right. So remind you what the adjacency effect is. I have my sensor over here. And my sensor is designed only to see this red circle. And that's all it is going to see. I'm looking down at that red circle, and if there's no stray light, there's no problems with the optics, I will only see photons coming from that red circle. But the reason I've made it red is because I want it to be a different reflectance than the other material, green. So maybe this is, actually I don't think I know anything that's red colored that's natural.
I'm outside.
Flowers.
Flowers, yes, thank you. We have a flower garden. See, that's the difference. We talk about people who think in rocks, and people who think in beauty. So there's beauty and there's rocks. The question I used to ask when I taught was, so how many scientists do I have and how many engineers do I have? And it was always interesting to watch how they would self-separate. The scientists would think they were engineers, the engineers would think they were scientists. And both sides thought the other were not very smart. So, geologists are okay. They're fine.
I'm not a geologist.
It's all good.
Oh, that's right.
Engineer, scientist.
See? So we have our flower bed here of geraniums or something that's a nice beautiful red surrounded by just grass. And the problem is that photons can still come down from the sun and they can bounce off of the green thing and they can bounce up and come over and act like they came from the red thing. Same as they can come up and they can bounce off the green, come down, bounce off of the red, and actually come from the red. But this green stuff is affecting the final answer. And so it's this adjacent material that's causing us problems. And to kind of highlight it some more, get rid of the colored part and just talk in terms of black and white and black and white. And if I'm at the top of the atmosphere, and I'm looking at the white object, and I'm far enough away from the boundary that all I see is energy from the white. Everything that happens goes white to white to white, and I get an output. If I come over here to where I'm just looking at everything black, so I have black to black to black, I get an output. And the thickness of the arrow, so it's dashed here, that means I'm not getting a lot of radiance in this particular case. Over here I'm getting more radiance because it's a higher reflectance. Make sense? Now I'm going to look at some white material here that's surrounded by black. So I'm going to get some of the photons that are going to go black to the atmosphere to white to my sensor. I'll still get some white to white to white. But I'm not going to get as many photons. So over here, I got a lot of photons because it was off the white material. Over here, I'm not going to get as many photons because the black material is going to absorb a lot of them. So I get a reduction in the amount of energy that I get coming from this white surface. Same reflectance, same size, same everything. It's just I'm close enough to the boundary that I get a reduction in the total radiance because I do not have a uniform bright material. I have a bright area surrounded by something darker. And this black part here, the same problem, is now I'm going to get a higher radiance than I would expect because I'm surrounded by material that can bounce the light around better than I would expect it to do. So I'm going to get more photons than I would have expected if I had just all black everywhere. So if I have a dark material surrounded by bright, I end up with a higher radiance. And if I have a white material surrounded by dark, I get a lower radiance than I would get if I had a perfectly homogeneous scene in either case. And that's the adjacency effect. And Dr. Richter, that Martin knows, he is the person in adjacency effect correction. He goes way back. When I was first doing my PhD, that was the person that we all looked up to, and I'm still happy that he's continuing to work and everything else. One of the highlights was meeting him at a conference. So I sort of know what it's like still to be that young scientist and go to the conference and go, oh, I've read all of your papers, and the scientist is going, but it's a nice feeling to see the people who are doing that work. And so here we're looking at this small little area. There we go, up here. And it's tiny and it's surrounded by a lot of different stuff. So the question was, is that surround causing me problems? Is that giving me an adjacency effect? That all of these other people who are telling me the reason I have the significant difference in band 2, 3, and 4 is because of the fact that you're using a site that has an adjacency effect problem. So we went through the process. And the way we did this was we looked at our test site and we computed what the average counts were, and then we just started making circles larger and larger as we went out and computing the reflectance as you get to larger and larger areas to find out what the reflectance of the surround was relative to the region that we had. And then we had our typical atmospheric cases. So this is the ratio of the at-sensor reflectance of the surround to that of the test site. So it's a very simplistic way to look at it. But the point is that, and this is by season as well, and it's looking as a function of time and as a function of band. And the idea was that if you had a very large ratio, whether it be small, so largely different from 1, if you had a value that was different from 1 by a large amount, then you would expect you to have an adjacency effect that you might need to correct for. And it turns out, so let's start with band 2, because band 2 is one of our significant bands. Well, there was a little bit of an effect here in the early time after launch in the fall and winter and into the spring. And as near as we can gather, there was maybe just a little bit of extra vegetation than typical. But then it pretty much didn't have much of a difference. Band 3, this red one here. Again, early on there was some difference, but that wasn't when we were seeing the differences between the large and the small site. And it's not that large of a factor. Band 4, that one is one that, okay, that probably should have an adjacency effect. But band 5 didn't. Well, then you can explain that as maybe, well, you're a long enough wavelength that now the atmospheric effect isn't quite strong enough to make it a difference, so on and so forth. But it at least gave us an idea that maybe there's some of the effect is caused by it. You can do an adjacency. And the problem was that we went to the process of actually doing the adjacency effect correction, and it made no difference. We got the same kind of scatter, and we got the same disagreement. So we're still. And then we lost our money to do the small site work because they want us to do the big site work, and so we've never gone back and figured out why those few bands ended up giving an odd answer. But there was a process in terms of trying to understand through the studies the sensitivity of what's going on between the surface and the atmosphere. And what we concluded was that the small sites work pretty fine. There's no trouble with them. But what you want to do is make sure that you have at least a size that's 3 by 3 pure pixels, which means you need to have 4 by 4 or 5 by 5 so that you have this core of data. And the reason the 3 by 3 is important is because there is no sensor that has a 30-meter footprint. When they say it's a 30-meter pixel, it really means it's getting about 60% of its energy from that 30 meters, and it's going out to 70 or 80 meters for all of its to get a much larger area than what you think it should be to get that one pure answer. The asphalt, what's nice is it ends up being very similar in reflectance to typical material in the desert southwestern United States. It's sand, it's dirt, and there's not a lot of vegetation. So when you start looking at what adjacency effects are, it's a difference in reflectance. And if it's not a big difference, you won't see much of an adjacency effect. And then you couple that with low aerosol loading, we had all of those satisfied. So the weathered asphalt gave us the magic reflectants. What we're really never able to figure out is what caused the differences that we were seeing. We were just happy that we had a good result and that we learned a lot in terms of how you would pick out what sites are good sites for this. But most of it was that we could do a less expensive collection without loss of precision, and we could prove it through sensitivity analysis.